afternoon, ladies and gentlemen. Today we started with the topic that we are going to focus on today. That talks about the inverse trigonometric ratios. So I know that I had this class yesterday, and I'm also having it today. So in case you might be attending even when it is not your turn, I assume that the people that I'm with are seeing this for the first time. Okay. So let's start with the normal that we are usually exposed to. If you are expected, let's say, to use a calculator, and you have to find sine of 30 degrees. What you usually do, let me just make this a bit bigger, and you have also a pointer. Okay, and let me again point options. Right. So if you want the sine of 30 degrees, if you have a scientific calculator, well, the different scientific calculators actually, they differ obviously in terms of the way their functions are modeled. But normally on a calculator, you press sine, because the first thing that you need to do is to make sure that your calculator is in a degree mode, because the question is about sine of 30 degrees. So in that case, you press sine, you press 30 and equal to, then it gives you the answer. And then some other times you may be expected to find the angle given the ratio. Like for instance, if you are given that cos of theta is equal to 0.5, remember that you are free to stop me if there's any thing that you need clarification on. And then depending on the type of calculator that you have, you may press a second function and cos, and this is what will be reflected. And then once this is reflected, then you press 0.5, and then if your calculator is in a degree mode, you find that once you press equal to, then you are going to get 60. And because of your calculator being on a degree mode, we conclude that it means that theta is going to be arc cos of 0.5, which is going to be 60 degrees. Well, that is something that you are confronted with almost all the time. Now, there are other ratios for which you can be expected to find the inverse trigonometric relations, either equals inverse cos or inverse secant, inverse cosecant, inverse sine, or maybe even inverse tangent. Now, if you press your calculator doing the same as what we described earlier, you'll find that theta will be equal to 45 degrees. The inverse cos of half is 45 degrees. The inverse secant of root 2, for the first one, the inverse cos of 1 over root 2 is 45 degrees, and the inverse secant of root 2 is 45 degrees. The inverse cosecant of 2 is 30 degrees. The inverse sine of half is 30 degrees. It is something that you can check using your own calculator. But then how do we confirm that this is indeed going to be true? By saying the cos of that angle, 45 degrees, it must give us that number, 1 over root 2. And for the second part, it means secant of 45 degrees must be equal to root 2. And then cosecant of 30 degrees will be equal to 2. And then the inverse of sine of half, it will be equal to 30 degrees. Now, immediately by looking at this, you should be able to know that we cannot say inverse cos is the same as secant, because whenever you want secant of any angle, it will just give you a ratio or a number, if you like to put it that way. But when you want the inverse cosine, it gives you an angle all the time. So you cannot assume, for instance, that inverse cos is secant, or inverse secant is cos, or even inverse cosecant is sine, and so on. Because when you want the sine, you are not going to get an angle, but a ratio.
So,
now,
say, how do you type in a secant on a calculator?
How do you
type in a secant 45 on a calculator?
Basically, on a calculator, you are going to have cosecant of 45 degrees, get an answer, and then from there, you are looking for 1 over that. There is a button that says x to the power minus 1. If you press it, it will give you the secant. It is because the secant of 45 degrees is the same as 1 over cos of 45 degrees. That's why you are going to have to look for cos of 45 degrees, get an answer, and then you invert that answer. It will confirm that indeed you can get this. The same thing applies to cosecant. I know that they are not explicitly there in your calculator. So that's one thing to observe. The second thing that you must observe again is that when you talk about arc cos of 1 over root 2, the answer that you get is exactly the same as what you get when you look for arc secant root 2. So in other words, the relationship between the two is that if it is 1 over a, here it will be a. The same thing applies to cosecant and arc cosecant and arc sine. If it was arc cosecant of 2 and it gives you 30 degrees, it would be the same as talking about arc sine of 1 over 2. So that is why generally arc secant of a, it will always be the same as arc cosecant of 1 over a. Arc cos of a will be the same as arc secant of 1 over a. And the same thing applies to tangent and cot. Arc tangent of a, it will be equal to arc cot of 1 over a. That is one of the things that are important that we are going to be need as we proceed. Now, our topic here basically is inverse trigonometric functions. Now, there is an element of inverse and there is an element of function. If you want the inverse of y is equal to sine of x, the inverse you are always going to get by interchanging x and y. So in other words, the inverse of this, it will be x is equal to sine of y. So in other words, what used to be x now becomes y, and what used to be y becomes x. Like for instance, this point here, it is, if we look at this graph here, the graph of y is equal to sine of x. This point here is x is equal to pi over 2, and then y is equal to 1. If you want the corresponding point that is going to be part of the inverse, you look at a point like this one. You see, this point here, it is pi being equal to, it is pi over, it is going to be 1, because the highest point on this graph is always going to be 1. So it will be 1 and pi over 2. Remember that this one is pi over 2, 1. And the corresponding one will be interchanging those two so that it can be 1 and pi over 2. If you had pi and 0, the interval will be, the point that corresponds to the inverse is going to be 0 and pi. If you have this point, which is 3 pi over 2 and minus 1, the corresponding one, it will be minus 1 and 3 pi over 2. So it will be that one. So in other words, you start by drawing this graph, and then from there, to get this graph, you simply interchange all those points that you obtain from that. You interchange them, and this is what you are going to get. That satisfies the inverse part of it. Now, we also need to do something in order to make it a function. Like for instance, if you want to check if this inverse itself is going to be a function, you'll conclude that it is not, because if you are to draw a straight line, a vertical line, you see it is going to cut this inverse at many points. So to solve that particular problem, you confine yourself to an interval over which it will indeed be an inverse, so that this topic of ours will then make sense. Inverse trigonometric functions. So if you look at this point from minus pi over 2, if you focus on this graph of the inverse from minus pi over 2 to pi over 2, you realize that indeed over that interval, it is going to be a function. Because if you were to draw a vertical line, it will always cut that part of the graph at only one point. But this is not the only interval over which it is going to be a function. Also from pi over 2 up to 3 pi over 2, it is also going to be a function. Again, even from negative pi over 2 to negative 3 pi over 2, it is still going to be a function. So that is where now we shall be talking about this inverse function. We say y is going to be equal to that inverse function if firstly we interchange in that we say sine of y is going to be equal to x. And then secondly, we restrict our attention. So for conventional purpose, it will be from minus pi over 2 to pi over 2. In other words, we deliberately ignore that part, even if it is still true, and we also ignore that part, even if it is still true. So that is how we can draw the graph of y is equal to sine and y is equal to arc sine. So we define arc sine firstly in terms of knowing that it is the graph that comes from this original one, and it is obtained by interchanging x and y. That's why we say x is equal to sine of y, which is what we have here. And then that's why, again, we restrict the interval so that it can be a function. So the same thing applies to if you want to draw the graph of y is equal to cos of x. The graph of y is equal to cos of x is a graph like this. And then its inverse is going to be like this. But if you look at the inverse, it is also not a function. But then if you focus from 0 up to pi, this part of the graph, you realize that indeed it is going to be a function. Or if you focus from pi to 2 pi, from pi it is going to look like this, and then it is still going to be a function. Or even if you focus from minus pi to minus 2 pi, it is still going to be a function. But for conventional purpose, we are going to recognize the definition of this arc cos This inverse cos, sometimes it is called arc cos, the same way as this sine inverse, it's known as arc sine. Now that arc cos is going to be the inverse of this, and the inverse comes from knowing that we have interchanged x and y to have now x instead of y is equal to cos of y. That is, the interchange gives us that inverse, and then the restriction ensures that indeed it is going to be a function. Right, and then we can take this a bit further, and a similar thing is going to be applicable even in the case where we talk about the graph of y is equal to tan of x and then arctangent or inverse tangent. Again, if you draw it, I just want to leave it to you as an exercise. You realize that it's going to be a function on these intervals from minus pi over 2 up to pi over 2. So that is how we can justify the drawing of the inverse trigonometric functions. Right. Now, the next thing, again, that is important is for us to deal with the differentiation of inverse trigonometric function. And we can start with the arc sine. We want the derivative of the arc sine, or if you like, you can say the inverse sine. So in that case, you allow y to be equal to arc sine of x, so that we know that we are looking for dy dx. Now, if y is equal to arc sine of x, that what it means is that sine of y will be equal to x. That takes care of the part of the inverse, and then y must be between minus pi over 2 and pi over 2. That takes care of ensuring that it is going to be a function. But then if we have this type of relation, sine of x is equal to x. If we differentiate both sides with respect to x, then the derivative of sine of y is going to be cos of y dy dx. And the derivative of x with respect to x is going to be 1. So that if we make dy dx the subject of the formula, it will be 1 over cos of y. And then we know that there is this relationship that says cos squared y plus sine squared y is equal to 1. So if you want to make cos of y the subject of the formula, then it's going to be the square root of 1 minus sine squared y. But what did we say about sine of y? We said sine of y is going to be x. So that sine squared of y is going to be x squared. So in other words, the derivative of arc sine of x is going to be equal to 1 over the square root of 1 minus x squared. But I want you to look at this x squared with the eye that you ask yourself the question, what is it that we are actually squaring in order to get x squared? We are squaring x. And then what is on top is usually going to be the derivative of what you are squaring. Now it's important to listen to what I say here. I'm not saying the derivative of the square. I say the derivative of what you are squaring. So what you are squaring is x, then the derivative is equal to this. So that if we wanted the derivative of sine of f at x, not x necessarily, then it means where you had x, you will be having f at x, and then it will still be squared. And then from there on top, there will be the derivative of what you are squaring. So, and then we can then look at some examples as to how we can evaluate the derivative. Let's take this example. If y is equal to arc sine x squared, we know that it means in relation to this equation, our f at x is x squared. And then f prime of x, it will be 2x. Therefore, the derivative of arc sine of x squared it is going to be 2x over 1 minus x squared all squared, and it will be 2x over 1 minus x to the exponent 4. Right. And then
sir, please go back to the slide, to the previous slide.
The previous one.
Yeah.
Which one? This one?
Yeah, that example, the example number 1. Can you please explain the last time?
Okay. You see, but you understand this equation, isn't it?
Yeah, I understand.
Because that is the one that we have just derived, right?
Yeah.
It says the derivative of arc sine of f at x. Now, if you compare f at x with what we have here, we have arc sine of x squared. So can you see that in the place of f at x, we have x squared now?
Yes, yes. Oh,
but then in our equation, we need f prime of x. That's why we know that f dash of x is going to be 2x.
Oh.
And then from there, remember that sometimes you can write it in word arc sine, but what we actually mean is sine inverse.
Oh, okay.
It is just the direct substitution into this equation.
So can they say arc cos?
We'll take a look at some other examples.
Okay, sure.
Thank you. Right. Now, if let's say for argument's sake we want we are given that y is equal to inverse sine of e to the exponent x. What is important for us to know is that if we have arc sine and we multiply it by sine, it is like they are going to cancel out, with the result that arc sine of anything is going to be that thing. So that if we wanted to simplify this, it will be like arc sine of e to the exponent x is actually going to be e to the exponent x, as you can see. And then from there, looking for the derivative of arc sine of e to the exponent x is simply the same as looking for the derivative of e to the exponent x. And that derivative is simply going to be e to the exponent x. That is the answer that you get when you simplify this. But then if you want to use that equation that we have that side, in other words, if you want to stick to using this equation, it still needs to give you the correct answer. If you do it that way, we are going to say dy dx is going to be, remember there is a square root sign and then 1 minus, now my f at x in this particular case is sine of e to the exponent x. That's why I have sine of e to the exponent x here, and then you square it. On top, there must be the derivative of what you are squaring. And what you are squaring is sine of e to the exponent x. And if you want the derivative of sine e to the exponent x, the derivative of sine is cos. It will be cos of the same angle multiplied by the derivative of the angle, which is e to the exponent x. And then this will be the same as having e to the exponent x cos of e to the exponent x, and in the denominator we shall be having 1 minus sine squared e to the exponent x. Again, if we use the relationship that says cos squared of anything plus sine squared of anything is equal to 1, then it means that this thing that is in the brackets is actually going to be cos of e to the exponent x. Then it will cancel with that 1, so that the answer is still going to be e to the exponent x. So here
how did you get the cos ex at the bottom?
I'm not very good at writing. Let me just see if I can try and write something. Pen. I'm using I'm using this equation. Sorry. Oh, now what have I done? Okay, I'm using. Let me see. Pointer option. Pen. I wanted a pen. So remember that there is this relationship that says sine f sine squared f at x plus cos squared f at x is equal to 1. You know this identity, isn't it? So in this particular case, if you want to make cos the subject of the formula, we are going to say cos of f at x f at x is going to be equal to the square root of 1 minus cos. That's what I've used here. I'm sorry, I'm not, I still need to improve my writing using this. But I'm simply I'm taking this from cos squared e to the exponent x plus sine squared e to the exponent x is going to be equal to 1. So if I want to make cos the subject of the formula, like here, I'm going to take this sine squared to that side, and cos it will be the square root of this. That's where I get it from. And then it's going to cancel with the 1 on top. And then only e to the exponent x is going to be left. Another example. If we are given that y is equal to arc cosecant 1 over the square root of 1 plus x, and then we have y is equal to, and now we go back to the very first observation, and we go back to the very same observation of saying if we have arc sine of a, it will be arc cosecant of 1 over a. Arc cos of a is equal to arc secant of 1 over a, and so on. So we are going to apply that one in order to simplify this expression, so that now we are then going to have, no, I think I have to go back. Right, so that if we talk about arc cosecant squared, it will be the same as arc, now arc cosecant squared is the same as arc cosecant all squared. But then arc cosecant 1 over 1 square root of 1 plus x is the same as talking about the arc sine of, then you invert this part. Then it becomes a square root of 1 plus x. And then when it comes to finding the derivative of this, we know that it is going to, because now this is squared, it will be 2 times this to the power 1 multiplied by the derivative of what is inside. Now the derivative of arc sine of this, it will be we are going to have this, and then from there we are going to have 1 minus, and then it will be square root of 1 plus x all squared. So what you are actually squaring is the square root of 1 plus x. And then square root of 1 plus x is the same as 1 plus x to the power half. So its derivative will be half times 1 plus x to the power negative half. And the negative half means now the square root is going to be here in the denominator. And then from there you can simplify this to say, okay, this 2 is going to cancel with that 1, and this will be your answer.
I say, can you please explain again?
Okay. You see, y is equal to arc cosecant. Do you understand why I have written it as arc sine of square root of 1 plus x?
No, sir, I don't understand. Can you please?
Or it is why you want to understand. What I'm trying to say is, if you look at the previous example, you see, if we are talking about, let's say, arc cosecant of 2, it is the same as arc sine of 1 over 2. In other words, if you change from arc cosecant to arc sine, whatever number you had here, you must have 1 over that number. The same thing applies to if you have arc cos 1 over something, it will be the same as arc secant of that thing over 1. You interchange this. So we are confronted with the same situation here. We are confronted with the same situation. Here we had arc cosecant 1 over the square root of 1 plus x. It was arc cosecant, but then it is squared here. Now, arc cosecant squared is the same as talking about arc cosecant of that thing, and you square everything. But what is in the brackets? You see, arc cosecant, if you want to change it to arc sine, it will no longer be 1 over the square root of 1 plus x, but it will be, you invert that, it will be what is in the denominator comes on top. And that's why it is going to be this.
Oh, I understand, sir. Yeah.
Okay. Right. Thank you. And then from there now, if y is equal to this, now it will be a question of saying, okay, this is arc sine of this all squared. So that's why dy dx is going to be 2 times that to the power 1. And then multiply, then we come inside. And the derivative of arc sine, we are going to have the square root sign, 1 minus, and then whatever we have here is the very same thing that we are going to square. But then what we are squaring is square root of 1 minus x, and then from there we want the derivative of what is inside. So it will be 1 over 2 into root 1 plus x. That is the derivative of this one. And that's why our final answer is going to be this. Obviously, if you square this, it's going to be 1 plus x. And if you have minus outside, the ones are going to cancel out. And here it will be the square root of negative x. So that will be your final answer. Don't be deceived by the fact that I'm talking about the square root as if I'm talking about the square root of a negative number. No, not necessarily. Because if x itself is negative, then negative x is going to be positive. So this can exist. Another example.